today's lecture, we will discuss about mathematical expression of active recovery voltage. So, before going in the detail about mathematical expression, first of all, we will discuss again about active recovery voltage. As you know from my previous lecture that I have discussed the active recovery voltage in great detail. So now I'm repeating it here for the better understanding and as a refresher to understand the mathematical expression. The active recovery voltage is a component of the transient recovery voltage that appears across the circuit breaker contacts after interruption of a fault. So from this figure, we can understand what is transient recovery voltage and what is active recovery voltage inside it. So from here to here, starting from here, the zero crossing, current zero instant, from this point all the way from here to here and up to this point, this whole area is actually indicating the transient recovery voltage, which is TRV. Fine. So now we have to basically point out in this area where is the active recovery voltage. This transient recovery voltage basically comprises of three voltages. One is active recovery voltage, the other one is recovery voltage, and the one another is restriking voltage. So again, these things have already been explained in my previous lecture. So now what is the active recovery voltage? So from current zero, starting from current zero up to this point, the voltage from here to here, this voltage is known as active recovery voltage or ARV. So from this point to this point, the voltage is known as restriking voltage. And from this point to this point, the voltage from this point to this point, the voltage is known as recovery voltage. So from here to here, the overall voltage is known as transient recovery voltage TRV. And this transient recovery voltage is further disintegrated to three types of voltage. One is active recovery voltage, other one is restriking voltage, and the last one is recovery voltage. So hope you are clear what is active recovery voltage out of these three disintegrated types of transient recovery voltage. So this active recovery voltage, as discussed in the previous lectures, is influenced by the system's inductance and capacitance, which are the storing elements and typically modeled using second order circuit or RLC. When deriving active recovery expression, constants such as K1, K2, and K3 are often introduced. And what is the significance of these constants in the overall equation of active recovery voltage that we will also discuss in the today's lecture. So now we will start with the mathematical expression for active recovery voltage. But while discussing the mathematical expression for active recovery voltage, we usually discuss is it in two contexts. Uh, One is classical power system protection, and the other one is simplified scalar representation of the active recovery voltage. So, if we will discuss or say that we are discussing about the classical power system protection, in this context, the active recovery voltage is typically represented as a time varying waveform. So, the equation is the active recovery voltage equation is actually dependent on time. This equation is derived from system's LC response after current interruption, and the standard analytical active recovery expression is then written in this form, which is dependent on time. So this is one context of indicating or representing the active recovery voltage, which is dependent on time and which changes with the time. The other context, which is usually known as the simplified scalar representation, it is used in the older systems or by the vendors or the manufacturers of power system or the protection equipment. And it is also a simplified analytical model for finding out the active recovery voltage because it is based on approximation as a single peak value. So here active recovery voltage peak is K1, K2, K3 Vmax sin phi. So this value of active recovery voltage is basically the peak value that can occur in any case. So the model or whenever the ARV is discussed in form of this equation, it means that they are discussing about the peak value of active recovery voltage. And whenever the model is or the active recovery voltage is written in this form, this means that they are basically discussing about the change in active recovery voltage with the change in time. So naturally, it is clear that most of the time the peak values are being utilized by the industry guys or the manufacturer of the equipment. So to have the peak value that may occur in any worst case scenario and manufacture a circuit breaker by having the in mind the peak disturbance that can occur on the system. So usually the current values are also important and they are being utilized by the researchers or the simulations or the power planners so they can check the response of the circuit breaker at various different instants. So this is uh, a main difference between both of them. So which one is correct? If you are modeling ARV over time or studying TRV, transient recovery voltage for simulation or academic purpose, use the time domain expression. And if you are calculating maximum ARV for specification or design limit, such as in the field or practical life, the simplified scalar equation with K1, K2, K3 Vmax sin phi is valid as an approximation. So I hope this is clear to you that where each one of this equation can be utilized or what is the importance of these models for various applications. So now this is clear to you. First, we will discuss the mathematical expression of active recovery voltage for the classical power system model and derive an equation for them. So while driving an equation for active recovery voltage, while driving an equation for active recovery voltage, we will keep some assumption in our mind. So the first assumption is the fault current is interrupted at current zero. The second assumption is the source can be modeled as an inductor L and a capacitor C from the breaker terminals to ground. No resistance is considered. Therefore, we are taking it as underdamped or lossless LC circuit. And the initial voltage and the current conditions are used to determine the constants. So based on these assumptions, we will calculate the classical mathematical expression or we will derive the classical power system protection equation for active recovery voltage which is dependent on time. So starting with the second order differential equation of this circuit, simplified circuit in which we have L and C are connected in parallel with the circuit breaker or a switch, and suddenly it opens. So as it opens, so therefore the source voltage becomes zero at right at that instant. So that we can write the equation at that time is equal to d square Vt over dt square time plus 1 over Lc plus Vt. So this is the second order differential equation. We know that omega naught is equal to 1 over under root Lc. So we can replace 1 over Lc here in this equation by omega naught. As 1 over under root Lc is equal to omega naught, so 1 over Lc will be is equal to then omega naught square. So therefore we have replaced 1 over Lc here in this equation with omega naught square here. So the general solution of this differential equation is Vt is equal to K1 cos omega naught t plus K2 sin omega naught t. You are aware of this fact that for having the value of V2, Vt, we must have the values of K1 and K2. And K1, K2 can only be find or determined by using the initial conditions. So now we will apply here the initial conditions for this problem and then find out the value of each K1 and K2. So there are two initial conditions in this problem. First is that at the moment of interruption, when the interruption occurs, that is at time t is equal to 0, the voltage across the breaker is V naught is equal to V0 is equal to V naught. So suddenly when the interruption occurs, so the voltage across the breaker becomes V naught. Fine. And this V naught is what? This V naught is the supply voltage. Since the current is zero after interruption, the change in voltage with time, because the current is zero after voltage, so the voltage change with respect to time at time zero is equal to zero. So these are the two assumptions that we will utilize to find out the value of the K1 and K2. First, when we apply the initial condition 1, that is at the moment of interruption when the V0 is equal to V naught. So for that case, we will replace V0 or V of t with V naught and replace the t is equal to 0 wherever the t comes here in this equation. So t is equal to 0 in this equation will become 0. T is equal to this will become is equal to 0. So this will become sine 0 and here we have cos 0. Cos 0 is equal to 1 and V2 is equal to, you know that Vt is equal to V naught. Therefore, the K1 is equal to V naught. So you can look here. When we place t is equal to 0 and t is equal to 0 here, this cos 0 exists, but this sin 0 never exists. So V naught replaced with V naught, V0 replaced with V naught, V naught is equal to K1 becomes. Then we will apply the second initial condition. In the second initial condition, we know that dV by dt at time t, but we know that the time t is equal to 0. At t is equal to 0, you know that this will become sine omega naught of 0, omega naught cos omega naught of 0. So again, we have sine 0 here and cos 0 here. So this will become equal to 0. And here we have K2 omega naught cos 0 is equal to again 1. So we are left with K2 omega naught. K2 omega naught is equal to dV by dt at 0. But friends, we know that at initial condition dV by dt at time t is equal to 0 is equal to 0 because there is zero current after the interruption. So therefore, we will replace dV by dt at 0 by 0. Ultimately, whatever we get after simplifying here, that is K2 omega naught, that will be is equal to 0 and then K2 is equal to 0. So now the value of K1 is equal to the value of K1 is equal to V naught and the value of K2 is equal to 0. By putting this value of K1 is equal to V naught from here and K2 is equal to 0 from here in this equation, So this will become Vt is equal to K1 because, now K1 is equal to, you know that K1 is equal to V naught. So Vt is equal to V naught cos omega naught. However, K2 is equal to 0. So this part of this equation will become is equal to 0. So this part of this equation will not become. So now Vt is equal to V naught cos omega naught t. So therefore, we have Vt is equal to V naught cos omega naught t. So this is known as the natural response of the system. However, it only considers the LC response and does not yet includes the reapplication of source voltage. And why the source voltage reapplies? Because after the interruption, the system voltage begins to reappear across the open breaker contacts, which is usually known as restriking voltage, and the whole phenomena is known as transient restriking voltage. This forced response due to the power system voltage is typically modeled as V forced T is equal to K3 times 1 minus omega T, and this forced response usually occurs because of the capacitors and inductors or the storage elements present in the circuit, as I have already explained in my previous lectures. So the overall response of the system will become is equal to natural plus force response. So the natural response is equal to V naught cos omega naught t, which is here. And you know that V naught is equal to K1. So we have replaced here V naught with K1. And the other response, which is force response, it is equal to K3 1 minus omega t. So when we will superpose with each other, so they will add in one another. So the active recovery voltage at time t is equal to now natural plus force response. If we consider the damping, or if there is a damping effect, the natural part becomes, so then the natural, because why? Because due to the resistance, now it will have a phase shift. So it will become K1 E minus alpha t sine omega dt plus phi. So because of that damping, it is now converted to sine omega dt plus phi. Fine. So now we will replace, while considering the impact of damping as well, cos K1 cos omega naught t with K1 E minus alpha t sine omega dt plus phi, and where the value of alpha is equal to R over 2L, which is also known as damping factor, and omega d is equal to omega naught square minus alpha square. So if we will replace this here in this equation, so this equation has the final expression as Vt is equal to K1 E minus alpha t sine omega dt plus K2 plus K3 times 1 minus cos omega t. So so in this form, we can calculate the classical active recovery voltage expression used in transient recovery voltage. So whenever we want to calculate the transient recovery voltage and in the form of classical power system protection or have a time indication as well. So for that case, the active recovery voltage can be calculated using this equation, which is a more advanced and more modern equations to calculate the active recovery voltage. Now we will discuss the older form of this equation or the older representation for the active recovery voltage, which is also known as the simplified scalar representation because it is based on the peak value. So we know that the phase to neutral system voltage is usually represented with V volts, and the maximum, if we want to find the maximum value of the phase voltage, we usually multiply it with under root 2. So it will become the peak value. The active recovery voltage between phase to neutral is then equal to under root 2 V sine phi, which is equal to V max sine phi. The general expression for active recovery voltage is then given by VR is equal to K1, K2, K3, V max sine phi. So the simplified scalar representation for active recovery voltage is K1, K2, K3, V max sine phi. So what is K1, K2, and K3? So K1 is basically the demagnetizing component, and its value should be lesser than or equal to 1. So, what is this demagnetizing component? The demagnetizing factor is not typically added in the mathematical expression of active recovery voltage for conventional high voltage circuit breaker transient recovery voltage modeling. However, if the demagnetizing factor is included, it is likely due to specific conditions involving transformer fed faults or switching transients where magnetic core saturation, residual magnetism, or inrush phenomena affects the voltage recovery. So I hope it is clear to you where this K1 or the demagnetizing component is considered and in which type of the problem. So the K2 is basically indicating that a phase factor and indicates whether the symmetrical fault is grounded or not. So if the we have a grounded fault, then the K2 is equal to 1. And if we have an ungrounded fault, then the value of K2 is equal to 1.5. Similarly, we have another factor which is known as K3, and its value is 1 if phase to ground value is required, and its value is under 3 if between two lines is considered. So I hope it is clear to you that what is active recovery voltage, what are what are the mathematical expression for active recovery voltage in how many contexts that we can represent the active recovery voltage. So I hope this lecture made it clear to you the mathematical expression and the derivation of active recovery voltage. Thank you very